We all know about rockets. We also all know that they're extremely difficult to make and launch, with the term rocket science often being synonymous with something very complicated or hard to understand. In this speech, however, I'll be teaching you about one of the simpler aspects of rocket science, so then hopefully you can have a basis for researching more difficult aspects of the field. I'll tell you about the three people who made rocketry what it is today, and I'll break down the rocket equation, and I'll tell you what its parts are, what it solves for. So the history of rockets is long and complex, with the Chinese first inventing them around 1st century AD and using them for fireworks and entertainment. So we'll just focus on the early and mid-1900s. This is Konstantin Tsiolkovsky. He's one of the first men to really start exploring rocket science. He was the first person to come up with the famous rocket equation, also called the Tsiolkovsky rocket equation. So in 1926, the first liquid fuel rocket was built and tested by American professor Robert Goddard. The professor also made several calculations on rocket flight and predicted the moon landing. He received some negative attention for this, including the New York Times publishing an editorial saying it was absurd and scoffing at the idea. This is Hermann Oberth, and he's the only of the three men to see his work put into action. Oberth explored the theory of vacuum-propelled space propulsion and multi-stage rockets. His legacy was tainted, however, whenever he started working with Nazi Germany in World War II to make V-8 rockets for the bombing of London. These three men together are known as the fathers of rocketry because their work was so influential on the rockets we have today. So now I've told you about the fathers of rocketry, let's move on to the equation and explore what it means. This is the rocket equation. It can be known as the Tsiolkovsky rocket equation, or just the Tsiolkovsky equation, and it may look really daunting at first. The equation is used to solve for delta V, which I'll explain with the other components. So delta V, this little thing right here, is change in velocity. It's how much velocity or speed you can obtain before your rocket runs out of fuel. So let's say you have a rocket, right, it's sitting in space, and you fire your engines in one direction until you're traveling around 200 meters per second. You've changed your velocity from 0 to 200, and that's your delta V. That's your change in velocity. It'd be 200 meters per second of delta V. Now it's important to note that if you change your delta V 200 meters per second that way, and then you flip around and slow yourself by 100 meters per second, your speed in that direction is 100 meters per second. But your delta V is not. Your delta V is 300 meters per second. Because you changed it 200, then you flipped around and changed it 100. So the next value of the equation is this thing right here. It's the fuel ratio. It's how much fuel is in your rocket compared to empty rocket. This top one, M dry, refers to the mass of your rocket without fuel. It's an empty rocket. It's been burned out. While this one down here, M wet or M start, it's the same thing, refers to your rocket at full mass on the launch pad full of fuel. The actual units of these two numbers that you measure them in, it doesn't matter because the ratio is what you need. So you can measure it in grams, kilograms, pounds, whatever you feel, whatever you want, as long as they're consistent, as long as they're the same number, because you want the ratio to be the same. You want it to be the same. This ln in front of the parentheses is the natural logarithm function. It's an algebraic function that deals in true exponential growth and decay. So like as the rocket burns, it loses fuel, and that makes it lighter and better and easier to propel. And this function right here, the ln function, represents that. And the final value, this VE right here, is exhaust velocity. It's how fast the gases are coming out of the nozzle, out of the rocket. And this value comes from multiplying ISP by the gravitational constant. Now these sound scary at first, so let me break it down for you. ISP is essentially the efficiency of your fuel. It's how much bang you get for your buck. The higher the ISP, the better your delta V outcome is, and the less fuel you can store. Less fuel is better because it's a lighter rocket. And each fuel type has a different ISP. The highest fuel type is liquid oxygen and liquid hydrogen with an ISP of 455 seconds. The lowest is solid fuel, which is fuel you see in model rockets, but there's also hydrazine and kerosene, which can be problematical if you want to store them. It can present problems. The Earth's gravitational constant, which is denoted little g, as opposed to big G, which is the universal gravitational constant, in a much smaller number, is only around 9.8 meters per second. It refers to the acceleration at which an object will experience under Earth's gravitational pull. So you multiply the ISP by the Earth's gravitational constant, you get your exhaust velocity. Then you have all the numbers to plug it in, solve for your change in velocity. This is how much your rocket can go before it runs out of fuel, which is really important if you want to get to orbit, get to the moon. So now we talked about what the rocket equation is, what its variables represent, as well as who made rockets and spaceflight possible in the first place. Note that I only scratched the surface of rocket science, and this all is a very little component in a giant field, and there's so much more to learn and discover, so feel free to do research on your own. Thank you.